Okay, testing, we're good. All right, welcome everybody to the very last lecture. Thank you all for sticking around for this long. All right, so we have previously talked about possible ideas for what dark matter could be. Last time we talked about the different complementary ways of finding dark matter that if it interacts with the standard model, which is motivated somewhat by the WIMP picture but extends beyond it. So today I want to talk about indirect detection, which generally means that we look for standard model particles that were produced through some dark matter physics, and we do this largely using telescopes. So this is an area where a lot of my personal research focuses. So just to pitch that, we have a lot of really good telescopes, covering a lot of different energy ranges for photons. We have neutrino telescopes as well. We have missions that can measure the flux of cosmic rays, charged particles. All of these are possible products of dark matter, and we basically get the data for free from the astrophysics and astronomy community. So what I want to talk about today is first, just generally, if you did have dark matter that was interacting with the standard model in such a way that you could produce standard model particles from the dark sector, then just broadly speaking, what kinds of effects could we expect that to have on cosmic history? And it turns out that this is a way to put very generic constraints on dark matter decay and annihilation. So I'll talk a little bit about that. Then I want to say, okay, there are many possible channels for dark matter indirect detection, all of which are being pursued at the moment. But in particular, photon and neutrino signals are nice because those particles are not charged and they travel to us in straight lines. Cosmic rays are also a good detection channel, but the difficulty there is that you can't tell where they came from in the first place, so it's a bit more difficult to distinguish charged particles that came from dark matter annihilation from charged particles that came from conventional physics. But both are really interesting search strategies. All right. So let me begin by just saying a little bit about dark matter annihilation in the early universe. So just recall from last time, our picture here is that the kind of constraint that we're interested in could come about from two dark matter particles colliding. Something happens, we don't know what. Standard model particles, two or more, are produced. So if this kind of process can happen, we talked about earlier in the week on how this kind of process in thermal dark matter models could naturally explain the abundance of dark matter. So let's take that as our benchmark. Just ask, if you had thermorelic dark matter, what impact would that have later in the universe? So after freeze out, so we know what it doesn't do. The definition of freeze out is that after the relic density is frozen out, this annihilation process is no longer having a significant effect on the density of dark matter. The density is asymptotic, it's just fixed. Any remaining annihilations have to happen at a rate, on average, less than one the average dark matter particle is not going to annihilate in a Hubble time after freeze out. That's what freeze out means. But just because the average dark matter particle isn't annihilating doesn't mean that these residual annihilations can't have some interesting effect on the universe. So let's just think about scaling relationships here. So we know that after freeze out, the dark matter number density is just going to scale like the scale factor to the -3. So suppose I want to look at a measure of annihilations, could be the number of annihilations per co-moving volume in some Hubble time. Well, so the rate of annihilations is going, the number of total annihilations is going to go like the cross-section times m squared. The size of a, actually, let me not say annihilations per co-moving annihilation volume, let me say annihilations in a co-moving volume in a Hubble, over the course of a Hubble time. So this is my rate of annihilations per unit volume, but my co-moving volume is getting bigger physically as the universe expands. So this is going to give me a factor of a cubed, and over the course of a Hubble time, so this is my rate per volume, this is my rate of annihilations per unit volume per unit time. So the physical size of the co-moving volume is growing like a cubed, and the time scale for a Hubble time is going like h to the minus 1. So we know that n squared, it's like a to the minus 6. So this rate is going to scale like a to the minus 3, h to the minus 1, if sigma v doesn't change over time. So during radiation domination, how does this scale? So during radiation domination, we know that h is proportional to 1 over a squared. So this rate, so this is like the rate of dark matter particles annihilating, is going to go like a to the minus 3 times h to the minus 1, so that's like a to the minus 1. In matter domination, we have h goes like, have h squared goes like a to the minus 3, h goes like a to the minus 1.5, so this rate is going to go like a to the minus 1.5. So this rate, so this is one measure of, so this number of annihilations, which is going to be proportional to the power you're injecting from dark matter annihilation if they're relativistic. A given annihilation is going to convert the mass energy of the dark matter into standard model stuff. So the power injected from dark matter annihilation over a co-moving volume over a Hubble time is also going to scale like this. Now, at freeze out, by definition, like immediately before freeze out, what's happening is that an order 1 fraction of the total dark matter is going to annihilate in a Hubble time. So the amount of dark matter per co-moving volume is approximately constant after freeze out. So this rate at freeze out, this annihilations over a co-moving volume over a Hubble time, is going to be of order 1. So at freeze out, this quantity is order 1, i.e. order 1 fraction. Okay, so let me be a little bit more specific about this, because this quantity is proportional to the quantity that I'm talking about. So fraction of dm annihilating per Hubble time is order 1. Okay, so at times after freeze out, the fraction of dark matter that annihilates per Hubble time is going to just scale like 1 over a until matter radiation equality, and then it's going to fall a bit faster, like a to the minus 1.5. So what does that mean? So let's take an example mass scale. So if we considered 100 GeV dark matter that's annihilating with the thermorelic cross-section, which is just sort of the classic WIMP picture, then we said when we talked about freeze-out that the ratio of temperature to the dark matter mass at freeze-out was about a factor of 20. So we say take 100 GeV dm, freeze out happens at a temperature for the universe around 5 GeV. So now let's look at some later epochs in the universe's history and try to understand how big this fraction is. Well, Big Bang nucleosynthesis. Does anyone know roughly what the temperature of the universe is around Big Bang nucleosynthesis? Yeah, about 1 MeV. So it's like similar to the neutron-proton mass difference. So at BBN, T is about 1 MeV. If we ignore the changes in G star over time, which in this case is not going to be a fantastic approximation because this is before the QCD phase transition, but as an estimate it's fine. If we ignore the changes in G star over time, we know that temperature basically scales as 1 over A. So this corresponds to a factor of 5,000 in temperature between these two epochs. So between freeze out, this is during the radiation dominated epoch. So that means at this point, this quantity has fallen by a factor of 5,000 since freeze out. So a fraction of the 1 in 5 times 10 to the 3 of dark matter is annihilating. So what does that mean if this is... Okay, so 1 in 5,000 dark matter particles, 1 in 5,000 of the mass contained in dark matter. That's about 10 to the minus 3 of the total matter in baryons, right? So this is 10 to the minus, so there's about 5 times as much dark matter by mass as there is baryons. So this is about 10 to the minus 3 of total mass energy in baryons is being liberated per Hubble time. But, so the mass of a baryon, the typical mass of a proton or a neutron, is about 1 GeV. So this means that about 1 MeV of energy is being liberated by this thermal annihilation. So at this point, for this kind of completely bog standard scenario, 100 GeV dark matter, freezing out thermally, just annihilating with no velocity dependence, no momentum dependence or whatever, we're seeing the dark matter annihilation around nucleosynthesis would be providing an amount of energy for every baryon in the universe that is comparable to the neutron-proton mass splitting, that is comparable to their temperature at this time. So that gives you an indication that it's quite plausible that Big Bang nucleosynthesis could give you meaningful constraints on dark matter annihilation at this time, or the dark matter annihilation could potentially perturb BBN. And if you want to learn more about dark matter perturbing BBN, there's an old somewhat old, but pretty good review by Jadamczyk and Pospelov. There are more recent papers, but if you looked at this, will give you the background. So this sketch also tells you that if you have lighter dark matter that freezes out later, this number will be smaller, and a larger amount of energy will be liberated per baryon. So for very sort of standard parameter space, you can imagine having a non-negligible effect on nucleosynthesis, basically because, only a small fraction of the dark matter is annihilating. This is not an order 1 number, but it doesn't have to be. It's a question of what are you comparing to, and there are a lot of scales that are relevant in cosmology and in the standard model that are smaller than the mass scale of the baryons. Just want to pause here and ask, are people okay with this quick estimate? Any questions about this? This is the easiest way I know to see why dark matter annihilation is important in the early universe, and just get a quick estimate of how it's going to affect things. Is there a question there? Or is of the so we know. Okay, hang on. Okay, so it's 1 in 5,000 dark matter particles, but there's about 5 times much mass in dark matter as there is in baryons. So 5 times divided by 5,000 means about 1 in 1,000 of the mass energy stored in baryons, and we know that that's 1 GeV per baryon, pretty much. So that tells us that the energy being liberated is 1 MeV per baryon. I mean, you can also explicitly work out the density of the universe, put in the thermorelic cross-section, put in this mass, and you'll get the same answer. But this is the quickest way I know to just see how the scalings work. Any other questions? Okay, So next example, let's go forward in time to the epoch of the CMB. This is just a little bit after matter radiation equality, but almost all the scaling, since freeze out in this case is going to happen in the radiation dominated regime, so we can approximately just use this e to the minus 1 scaling. So this happens when the temperature is about 0.3 eV. I'm going to say 1 eV just because that's the level of accuracy that we care about in this problem. Okay, so in this case, so you can do the same estimate. We're going from 5 GeV down to so we're going from 5 GeV down to 1 eV. So that's 5 times 10 to the, so that's 5 times 10 to the minus 9. Sorry. Okay, so again, same argument. We know that there's 5 times as much mass density in dark matter as there is in baryons, so this corresponds to about 1 in a billion of the energy in baryons going away. Yep, okay, that looks right. So this is 1 in, so this is 1 in 5 billion dark matter particles, so roughly, sorry. 5 times, 1 over 5 times 10 to the 9 of DM will annihilate at this time. So that corresponds to roughly 10 to the minus 9 of energy in baryons added per h to the minus 1. So again, we know that the energy of a baryon is about 1 GeV. So this is about 1 eV per baryon on average. I mean, another way to say it is that this rate is just scaling like temperature. So yeah, so of course, what I'm finding is that I'm getting numbers that are roughly comparable to the temperature. But that means, so the ionization energy of hydrogen, which has our relevant scale at the CMB, is only about 10 eV. Right? I mean, it's 13.6 eV, but the order we're working, it's 10 eV. So this is enough to ionize 10% of the hydrogen in the universe. Now, our standard history for what happens at the CMB and immediately afterwards is that the universe goes from being almost completely ionized to almost completely neutral pretty fast. And after recombination, after the surface of last scattering, your baseline, what you're left with is a residual ionization fraction that is lower by a factor that is down at about 10 to the minus 3 or 10 to the minus 4. So if you go down a redshift 500 or 600, and this is predicting that 5%, that 5 or 10% of the hydrogen in the universe should be ionized by dark matter annihilation, then that's really ruled out. Like 1 in 1,000 hydrogen atoms being ionized is ruled out. So after recombination, expectation is ionization level drops as low as 10 to the minus 4. So if DM ionizes 10% of hydrogen, this is very excluded by just by measurements of the CMB. Because if DM ionizes a lot of hydrogen, you produce a bunch of extra electrons, as you said, I think on the first day, CMB photons love to scatter on charged particles, they love to scatter on electrons. So if you provide a bunch of extra electrons for them to scatter on, that will severely influence the CMB perturbation, the anisotropy spectrum that you see in the CMB. Now, I have hand-waved a number of factors here, which when you put them all together actually do buy you another couple of orders of magnitude. So it turns out that, again, as with the BBN example, if I make my thermal dark matter lighter, then there will have been less time during freeze-out, and this number will only go up. So this is a strong constraint on light thermal dark matter annihilating. So if you do the calculate, there's also another caveat, as well as the orders of as well as the factors of a few in the cosmological evolution. The other important factor of a few that I've missed is that this is just an energetics argument. This is just saying I have this much energy available. Whether it goes into particles that will actually efficiently ionize hydrogen is a different question. But when you work it all out, when you do a careful calculation, what you find is that the thermal cross-section, this simple thermal cross-section picture, so a constant thermal cross-section is ruled out by CMB measurements. For masses in the order of 10 to a few tens of GeV, if the dark matter doesn't annihilate just straight to neutrinos, so depending on final state. For most standard model final states, like if the dark matter was annihilating mostly to muons and muons and quarks of different flavors and tau leptons, you find that the limit is around 10 GeV. If the dark matter is lighter than about 10 GeV, then this simplest thermal scenario just doesn't work, and the reason that it doesn't work is because you predict too much ionization in the early universe. Now, there are ways out of this. Ways out of this include if my dark matter, ways out of this include if I go to neutrinos with a big branching ratio. Obviously, neutrinos are not good at ionizing things, so that gets you out of this. If your cross-section is not constant with respect to velocity, if your cross-section actually falls at low dark matter velocities, then this argument that I gave you will have some extra factors of A in it, and that will suppress this signal. If your dark matter, if it's not exactly the simplest thermal picture, so your dark matter has some primordial asymmetry, like the baryons and all the anti-dark matter annihilated away in the early universe, then that can get you away from these constraints. So there are a number of ways out of this, but it's just something to keep in mind. If you have a dark matter model that's below about the 10 GeV scale and you're relying on the annihilation cross-section to get you the right rate in the early universe, then these CMB constraints, you probably have to at least think about these CMB constraints and see how you're going to get around them. And as our host Marco Cirelli has pointed out, there are also models that are much more constrained by this than the simple constant picture. If your model increases the annihilation rate at low velocities, or you have formation of bound states or some other process that is stronger at low energies, then this constraint can actually be much stronger than what we've worked out here. Okay, so baseline of this is just by these simple scaling arguments, you can see that if you have something like thermal dark matter annihilation, then the subdominant dark matter annihilation after freeze-out can potentially have substantial effects on the thermal history of the universe and the ionization history of the universe. And so there are potential signatures and pretty strong bounds on that. In particular for light dark matter. These limits are all stronger for light dark matter, just because it froze out later. Now, we could carry this forward a bit further and just say, all right, let's suppose we extrapolate forward to the present day. Now, what fraction of dark matter is annihilating? Well, for this example that we took for 100 GeV dark matter, this quantity, this fraction that's annihilating, drops by this roughly 9 orders of magnitude between freeze-out and matter radiation equality. And then we argued that this would scale like a to the minus 1.5. So from matter radiation equality to the present day is a redshift factor of a few times 10 to the 3. So you raise that to the power of 1.5, that's something like 10 to the 5. So it's, did I do that right? Yeah, so if we take so fraction of dm annihilating drops roughly 9 orders of magnitude from freeze out to matter radiation equality. This is for the example. So it would fall about by 9 orders of magnitude from freeze out to matter radiation equality, and then about 5 orders of magnitude, if I've done that right, from matter radiation equality to now. If I'm remembering correctly when matter radiation equality is. So that corresponds to about 14 orders of magnitude in total. So out in the interstellar medium between galaxies, your fraction of dark matter that's annihilating ends up being like 10 to the minus 14, 10 to the minus 15. So occasionally people say, oh, like maybe I can have a case where dark matter annihilation really changes the amount of dark matter in my system. Well, if you want that, you need the rate to be like what it was at freeze out. So you need either a very strong velocity scaling or you need a really high baseline dark matter density. So this is in intergalactic space. Only 1 in 10 to the 14 dm particles will annihilate. In this example case, if you change the mass, you'll just scale this number appropriately. But today we have regions of much higher density than intergalactic space. So let's ask about like what fraction of dark matter near the Earth is annihilating. Because, as we'll see in a moment, when we try to think about signals that we could observe in the present day from dark matter annihilation, generally just the signal from the completely smooth dark matter density throughout the whole universe is pretty subdominant. Instead, we can look at the regions that grew from those little tiny perturbations early on, but are now very highly non-perturbative, much denser than the cosmological average density regions. So if you look at Earth, then you say the dm density is about 0.4 GeV per cubic centimeter. You can take the thermorelic cross section, sigma v. This is around 1 over 0.4, like 2.5 times 10 to the minus 26 centimeters cubed per second. And if you want to ask what fraction of dark matter in our galaxy has annihilated away in the age of the galaxy, so n sigma v, this is the rate for a single dark matter particle to annihilate. 2.5 times 0.4 is 1. So this is 10. So that's mass. So this is rho over m sigma v. So this is 1 over m times, that's 1 side times 10 to the minus 26 GeV per second. The age of the universe is about pi times 10 to the 17 seconds. our galaxy is not that much younger than the whole age of the universe, so if we just take its age to be somewhere in that ballpark, 10 to the 17 seconds. Then that'll give us times 10 to the minus 9. So if we've got 100 GeV dark matter, then something like 1 in 10 to the minus 11 dark matter particles would be expected to annihilate in the neighborhood of the Earth. Those of you who've been following may notice that the ratio between these two numbers is not actually the proper ratio between the Earth density and the critical density. That's because in this I made a bunch of approximations. I dropped a bunch of variations with G star. So really this number is actually more like 10 to the, I think this is more like 10 to the 16. So, but yeah, it's good enough to get a first estimate. So in our galaxy, so in our Milky Way, at our radius, roughly 1 in 10 to the 11 particles, 100 GeV DM particles would have annihilated over the age of the galaxy. So, to a pretty good approximation, unless you have an annihilation rate that really goes up at low velocities, you can ignore annihilation for purposes of understanding structure formation. But once you're looking not at the overall mass density, but at just the question of, well, can we see these photons? Can we see neutrinos or cosmic rays or other products? Then this rate where 1 in 10 to the 11 dark matter particles annihilates in 10 billion years may actually be observable. Just as in the early universe, it's not the fraction of dark matter particles that's annihilating, it's how that compares to other relevant scales in the problem. Yeah? If I put in m of 100 GeV here, that's 10 to the minus 2. Yeah. I mean, if I put in m of 1 GeV, this is 10 to the minus 9. I mean, this rate just scales simply with mass. All right, so having talked a bit about scaling over cosmological history, which is basically that if you've got thermorelic dark matter, then at any point where you have an observable, so at BBN is our earliest way to get observables of what the thermal history of the universe is doing. The CMB gives us another big chunk of information. In both of those epochs, thermorelic dark matter could potentially have meaningful and observable effects. And that's true for later epochs as well. There are potentially very interesting effects that dark matter could have around the epoch of reionization and the epoch shortly before reionization, which will hopefully be probed in the next few years to much better accuracy by experiments measuring the 21 centimeter line of neutral hydrogen. But let's now leave the early universe behind for a bit and say, okay, let's focus in on this present day. We have all these. We believe that there are clouds of dark matter around every galaxy cluster. We know that they're there by their gravitational effects. We know that there are smaller clumps of dark matter satellite galaxies of our Milky Way halo to the dwarf galaxies, so we can look for signals from those. So there are two questions that you need to answer in any indirect detection search. One is, what does your signal actually look like? What should you be looking for? Is it observable, given the range of parameter space that you're interested in? And the second question, which unfortunately is often quite a bit harder, is what are the backgrounds? Because what we're looking for here is stable particles that come about through dark matter annihilation. So this is our cartoon. DM particles come in, a miracle occurs, standard model particles come out. But in general, these standard model particles will subsequently be unstable and will decay through cascades. And at the end, what you're going to be left with is photons, is the stable standard model particles. So photons, neutrinos, electrons, positrons, protons, and antiprotons. And possibly some small fraction of more exotic things like of heavier nuclei, like antideuterons and deuterons and helium and antihelium. Okay, so this is our goal in indirect detection. Predict the signals in these channels from dark matter annihilation, figure out how to separate them from the background. So I want to talk mostly about photons and neutrinos just because cosmic rays are hard. If you want to know more about cosmic researchers, then Marco Zirelli, who's sitting down the front here, knows an awful lot about cosmic researchers with the AMSO2 experiment. He's written a number of the papers that I would point you to, so you can chat to him. So I'll just talk very briefly about that. So the reason why cosmic rays are difficult is because they're charged particles, which means that they follow highly non-trivial trajectories in the galactic magnetic field. Our galaxy is a sea of high-energy cosmic rays produced by astrophysical processes. We believe that these mostly come from supernova remnants. So any cosmic rays injected by dark matter are being injected into a sea of pre-existing cosmic rays. This is one reason why people talk about looking for anti-deuterons or anti-helium or something like that, because while they're hard to produce by dark matter annihilation, they might be even rarer in the galaxy as a whole. So backgrounds, our galaxy is a sea of cosmic rays, probably from supernovae. So when we talk about photons and neutrinos, I'm going to stress that these things travel on straight lines so you can see where they came from. So you can say, so if you see gamma rays coming predominantly from a dwarf galaxy where you know there's a lot of dark matter and very little baryonic matter, that would be a strong possible signal of dark matter annihilation. But with cosmic rays, it's very hard to do that because both the signals and the backgrounds are being scrambled by the ambient magnetic fields. So in cosmic rays, the key determinants of the key separation between your a dark matter signal and a background signal is largely just the spectrum. So CRs cannot generally reconstruct arrival direction, so we measure cosmic rays with space-based experiments that are in orbit around the Earth. At higher energies, you can measure them with ground-based experiments because when they hit the atmosphere, they produce a visible signal. So, energy spectrum provides a handle on signal versus background. So when you're dealing with cosmic ray potential signals, the critical things are, first, to understand how these things propagate through the galaxy. So approximately, this is modeled as a diffusion problem, as the cosmic rays diffusing through turbulent magnetic fields and simultaneously losing their energy by radiating photons or by scattering ambient photons up to high energies. So you need to understand this for both the signal and background. And this is an area where there's been a lot of work in the last few years to try to move beyond quite simple approximations that essentially treated the galaxy as a homogeneous cylindrical box. And there's been more data that's come in the last few years, as well from AMS, from the DAMPI experiment that China just launched, and from gamma ray experiments like HAWK, which hold out the hope of being able to refine these, of being able to refine our understanding of this. And the other thing that's important to understand is what does your dark matter signal look like, but also what are your background sources? And in particular, what are their energy spectra? So just as an example of this, there has been known since about 2008, so around about the time that I was a PhD student, at about your stage, that there's a large excess of cosmic ray positrons over what you would have naively expected. This was first observed by the Pomela experiment, which is an Italian experiment, and it was later, and is now being confirmed by the AMSO2 experiment, which is on the International Space Station. Now, the debate is not whether this excess is there. So this is a statement that if you plot the ratio, if you plot versus energy, the ratio of positrons over electrons plus positrons, then at first it falls with energy, which is what you would expect from the simple diffusive propagation models. But then at an energy around 10 GeV, it rises. And now the latest results from AMS sort of maybe seem to show it dropping off. This is a cartoon, you should look at the real plot. So, you know, maybe it goes like this, maybe it goes like this, and the error bars are larger. But there does appear to be an excess of high energy positrons. And back when this first came out, I and many other people, including some in this room, wrote papers saying, oh look, this could be a signal of dark matter annihilation. Dark matter annihilation should, like this peak here is still only about 15%, 10 to 15%. So dark matter annihilation should produce electrons and positrons in equal number. So if the baseline is way below 50%, then you would expect dark matter annihilation to push you closer towards 50%. However, those dark matter annihilation explanations, well, first, they tend to run into some problems with the CMB constraints that I mentioned, and with other constraints from gamma rays. If you were making that many positrons from dark matter annihilation, it's actually rather hard to hide it in other places. And the other question about this excess from the very beginning has been, well, are there astrophysical sources that can make a lot of high energy positrons? We know there are. Pulsars are spinning neutron stars. We believe they should be spitting out high energy positrons. But what we don't know, and haven't really had an observational handle on before maybe last year, is what is the energy spectrum of those positrons? If I want to be able to say, like, this is background and this is signal, it's absolutely critical that I understand the energy spectrum of my background. Whereas the contribution from pulsars, you know, it could look like this, it could look like this. We expect it could look like this. We expect it to have a cutoff at some point, but the location of the cutoff wasn't really known, and nor was the slope of the spectrum below the cutoff. So something that I find really interesting on this was that just last year, the Hawke experiment claimed to see high energy gamma ray emission coming from around pulsars, and that might give us a handle on the high energy electron and positron spectra that were being produced by those pulsars. Now, the only downside here is, as far as I know, that those papers have now led to a debate in the literature between the Hawke collaboration people who say these results prove absolutely that that this excess cannot be explained by pulsars, and a competing group that says no, these results prove absolutely that the AMSO2 excess should be explained by pulsars, where basically the difference is an assumption that they're making about how the diffusion coefficient varies spatially. So this is cosmic ray searches for dark matter are difficult. With new data, we may be able to get a better handle both on how the cosmic rays propagate and what the background sources look like and what their energy spectra look like. And there is this big excess, which eventually you would like a unified model of signal and backgrounds to explain one way or another, which could potentially be a dark matter annihilation signal, but it would have to be a pretty special dark matter annihilation signal to not have been seen in other channels so far. So that's the situation on cosmic rays. I could say more on that, but I want to draw a line under that for now. I can point you to references if you're interested in more, and instead talk about something that is in some ways easier, which are photons and neutrinos, where you don't have to worry about this diffusive propagation through the galaxy. And as a consequence, you also have a lot more information available to try to disentangle signals from potential backgrounds. So So that's where we're going next, but as I see that I've been talking for 45 minutes at this point, why don't we take a 10-minute break, and when you come back, we will talk about how to do searches with photons and neutrinos in the present day. Testing? Good. All right. So let's think about, so as I said, photons and neutrinos, they travel to us in straight lines. This means that we have more information than just the energy spectrum. We also know where they came from. Now, most of the time, we only know where they came from at the 2D level. We can tell where on the sky a photon is coming from, but we can't necessarily tell how far away it came from. There are some exceptions to that. The exceptions would be if you were looking at some kind of lion signal and the sources and the sources are at different redshifts, then you may be able, you can ask, is this signal consistent with coming from this redshifted source? But mostly we have 2D information. Okay. So I just want to ask, all right, suppose I've got some dark matter annihilation signal in some distant object. So here is me at Earth with my telescope looking out at the sky. Out here is some little clump of dark matter. I want to ask, what is the rate, as we did yesterday for direct detection, I want to ask, what is the rate of photons or neutrinos reaching me from this? So in this object, dark matter particles are colliding with each other, making photons. I want to ask, what is the rate of photons or neutrinos or other neutral particles that travel in straight lines and later convert into photons or neutrinos, such as axion-like particles seen at Earth from annihilation at a distance. Well, fortunately, since we live in a pretty flat universe, at least, and since locally we can just use Euclidean geometry, then for local sources, this is a pretty simple question, that just the rate of photons arriving. So let's suppose we want to look at annihilations at a distance r, annihilations in a volume dV at a distance r. Okay, because if I just ask what is I've got some annihilation happening out there, some one annihilation happening out there that produces n photons, then the number of photons that I see per unit area is just going to be the number of photons. You can substitute photons for neutrinos throughout here. The ideas are identical. I'm just going to write photons for convenience. I'm going to just multiply. I'm just going to divide by the area of the sphere that those photons propagate out through. So another way to say it is the number of photons that I'll actually see from the annihilation is the total number of photons produced times the area of my detector as a fraction of the area of the sphere that these photons have spread out to by the time they reach my position. Okay, but so suppose I have some volume of space with some density n, and I want to know the total number of photons from annihilation in that volume. So then, for annihilation, the number of photons from annihilation is going to be equal to the number of photons per annihilation So this is a particle physics question. This is how many photons are produced when these dark matter particles annihilate times the number of annihilations. And the second thing, we know this is just the rate of annihilations per unit time. So this is the rate of annihilations per unit time, per unit volume. So the total number of annihilations is going to be n squared sigma v times the time period over which I observe times dv. Now, there's one little caveat here, like I've been writing down n squared sigma v as an estimate for the number of annihilations, but if I'm talking about identical particles annihilating, I actually need to put a half in front of this, just because like if I look at the number of pairs, different pairs of dark matter particles, and they're all identical particles, the number is actually like n times n minus 1. If I had a number of particles n, then the number of pairs is n times n minus 1 over 2, where the factor of 2 means that you don't count as separate pairs like, 1 and 2 and 2 and 1. So, okay, so we have a factor of a half, which is just a combinatoric factor. If I was dealing with dark matter that was like half dark matter and half anti-dark matter, I'd only annihilate if I had a dark matter particle and a dark antimatter particle, and so instead I've had like n particles times n antiparticles. Okay, so the number of photons per annihilation, let's just call this n gamma. So this is a particle physics input. This could be 2 photons if it's just 2 dark matter particles come in, 2 photons come out. That's a signal that you can search for. And it has very low background because it corresponds to the photons each just having the energy of the dark matter. So it's a spectral line signal. But because we know dark matter doesn't couple very strongly to light, it's probably pretty subdominant. So a more common thing would be the dark matter annihilates into gauge bosons or quarks or something like that. And as the quarks hadronize or as the gauge bosons decay, then they produce some number of photons. So this could be 10 or 20 photons from those cascade decays without too much trouble. And if you want to know what this number is for common for the various standard model final states, if you Google PPPC for the MID, you will find that there is a very nice resource for indirect detection, and actually for cosmic rays as well, which among other things includes all the spectra for photons and positrons and electrons and neutrinos from decays of standard model final states. Alternatively, you can just run Pythia or a similar program to get this number for your model of choice. Okay, so the observed number of photons, so it's going to be area of the detector times time that you observe for. So this combination, effective area times time, it's called the exposure, and it just depends on your experiment. Then you're going to get, for identical particles, you're going to get 1 over 8 pi here times sigma v. We should write this n squared. This is the number density of the dark matter. We're probably going to know its mass density, not its number density. So we're going to get sigma v over 2m squared here. The little m is the dark matter mass. And then we're going to get a 1 over, so I'll just put the r squared in there. And we're going to get the a rho squared dv. Okay, so just as in direct detection, we traditionally split this up into, and I've dropped the n gamma. We traditionally split this up into different factors which reflect the different parts of the problem. Sorry? A is the area of your detector. Okay? So this is the total number of photons that your detector will see over a time delta t. So A delta t, this is about your detector properties. Okay. So then we have a, okay, so how will I phrase this? So, then we're going to have a particle physics factor. So this is your cross-section, your dark matter mass, and your spectrum of photons per annihilation. And then we're going to have a, it's going to be over m squared and sorry, I counted that 2 twice. There should just be 1, 2, because that 2 ended up in this 8 pi r squared factor. And then we're going to have a factor which is, so this describes distance to your source object and dark matter density in your source object. So this is stuff that you, if you have uncertainties on these, they're going to be astrophysical uncertainties. So this, okay, pi r squared, okay, good. Okay, so now, typically, when I'm looking at, okay, so a couple of things here. First is, if I want to extend this is just a count, but if I want to say the number of photons per energy interval, then if I'm dealing with something that's local enough that the photons are not going to significantly redshift between me and them, then I can also just write this. Just write this as a conversion factor between the spectrum that I see, at the telescope, and the spectrum at emission will just be exactly the same. If I need to take into account redshifting, I need to be a little bit more careful there. Okay, so now I am typically in this situation not going to be able to tell if a given photon came from 1 kiloparsec away or 8 kiloparsecs away, for example. So then I'm going to need to integrate over this parameter capital R. So the observed signal will be an integrate this over R, over the distance to my object. This may be a very trivial integral if I know that there's only a large density at one distance R. Like suppose I'm looking at a galaxy cluster, I know the distance to that galaxy cluster, then I can just approximate this by putting in the volume of this galaxy cluster and putting in the distance to the galaxy cluster. But generically, this is going to give me exposure times the particle physics factor times the integral of this volume factor. So this is going to be rho squared over 8 pi. So this is going to be like dr squared dr d omega if I pick a coordinate system centered at the Earth. These r squared factors will cancel out. So omega here is the angle subtended by the object, the solid angle subtended by this region, this omega region, as seen by me. So I can also talk about, so I can talk about this as a differential rate per unit solid angle that I look at. So, writing this as a differential rate, this tells me that the number of photons I see per energy, per area of my detector, per time that I observe for, and per solid angle that I observe on the sky is going to be given by this result. Okay, so here, so all the information on how long my detector looks for and so on, now to get an actual rate, I just need to take this differential rate, multiply it by the area of the detector, the time that I've looked at it for, and the solid angle on the sky that I observed. Of course, there can also be some angular dependence in this expression here, so you'll need to do an angular integral to do it right, not necessarily just a multiplication. So this is your particle physics factor. And this part of the expression, which contains information on the astrophysics, on the distribution of the dark matter density and how far away it is typically called the J factor. Now, there is an important thing to note here, which is that whether or not this factor of 4 pi is in the J factor is a convention that is not universal through the field. So if someone quotes a J factor, check their definition. I know of at least one paper in the literature where people cited a constraint on dark matter annihilation that was an order of magnitude weaker than it should have been because they messed up the J factor convention. Okay? And as a result, a lot of people had looked at that paper and sort of gone, oh, that constraint is interesting, but it's not really very competitive. Well, if you made it stronger by a factor of 10, it was very competitive. So, yeah, that's I found out about this when my grad student was writing a follow-up paper and showed me these constraints, and I was like, no, this is crazy. These constraints look stronger by a factor of 10 than this other paper, which did a very similar analysis. You must have a mistake. And then they came back to me and were like, yeah, well, it's this factor of 4 pi in the J factor conversion. So be cautious of this. So, but I mean, the J factor always contains this information. It's just a question of is there a 4 pi out the front or not? So just as an example, just as an example of the geometry, suppose we're looking at some spherically symmetric object on the sky. So here's our observer, here's our source out here. Such that the density is a function, the density in this source is just a function of distance from the center. So this is often the typical case that we assume when we're looking at a dwarf galaxy. So let's define, how do I want to define this? Let's define this as, let me call this L. Let me call this distance the distance from the center of the object to be L. So the density in the object is just a function of how far you are away from the center. So this is an assumption previously frequently used in the context of dwarf galaxies. So then, if you want to work out the J factor for that geometry, then what you want to do is, so this R here is distance from Earth to the point of annihilation. So let's say this is the center of object. Let's say the annihilation occurs out here. So for the J factor integral, we want to know what we want to know what this distance is. Let's say that the angle between this line and the center of the object is an angle theta. So we're using these polar coordinates centered on the Earth. We're going to choose our z-axis so it points to the center of the object, just because then that makes the phi dependence really simple. I'm going to say that this distance is, I'm going to say that like that distance is L. So then we have that, then we know this distance from the Earth to the center of the object, call that d. Then we can just use the cosine rule. This is rho squared of L So if you know like this is an NFW profile or whatever, this might be 1 over L squared. So L is just going to be equal to like the square root of R squared plus D squared minus 2RD cos theta. So what you would do in that case was you would take your density profile, rho as a function of L, you would just then plug this function into this integral and get an integral here, which was a function of cos theta. And then you'd have this differential spectrum of how many photons you expect as a function of location on the sky, as a function of theta, and also of energy. Now, okay, so first, any questions about this? This all makes sense. Definition of the J factor up to scary factors of 4 pi. Makes sense? Okay. So I'll just mention that, I mean, I've written this for annihilation, but another thing that you can look for in indirect detection that is really hard to look for in direct detection and terrestrial searches is decay of dark matter with a long lifetime. And for decay of dark matter, everything is essentially exactly the same as the calculation that we did for annihilation, except that instead of a cross-section that's relevant, we have a decay lifetime, and instead of a rho squared factor here, we just have 1 factor of rho because decay is a one-body process. So this is just dark matter decays into possibly many standard model particles. So if we write n gamma equals photons per decay, then the rate of decay is going to look like n over tau e to the minus t over tau, but we know that the lifetime has to be much longer than the age of the universe. So that tells us that this factor is just approximately equal to 1, and the decay rate just goes like n over tau, which is rho over m tau. So in the decay case, the signal rate in present day experiments is just the, so this is just going to give you 1 over m chi, 1 over tau. So the particle physics piece is the same, except that there's only 1 factor of mass and 1 factor of and the lifetime instead of the cross section. And so that is, here, let me just make sure that I do this right. So, and then the J factor piece is just going to look like this. Yeah. Good. Yeah, right. So, yeah, so, what I have in, yeah, I mean, so you're right. Like, I mean, in reality, this is a combinatoric factor that belongs here because, I mean, if you had, I mean, so this is just a question of convention. Certainly, I have seen papers, I have seen a number of papers where it's 1 over 8 pi, okay? There may be papers where it's 1 over 4 pi. You should check. If in doubt, I agree that conceptually that 1/2 factor really belongs over here because like whether it's 1/2 or 1/4 depends on whether you're dealing with Dirac or Majorana fermions. But yeah, I mean, there are definitely papers where it's 1 over 8 pi. I'm not sure how many, if any, there are out there, or it's just 1 over 4 pi. Sorry? Yeah, that's right. Yeah, the default presumption is that you're looking for a Majorana fermion or like some set of identical particles. Doesn't have to be true. Okay. So this works fine and allows you to predict what kind of spectrum you should see for if you don't need to take redshifting into account. If you do need to take redshifting into account, it is only a little bit more complicated. Actually. So if we do need to take redshifting into account, the issue is we need to account for the fact that the energy of the photons when they're first emitted is not the same as the energy when they're absorbed, and also the universe is expanded between the time of emission and the time of detection. So, including redshifting, I'll write this for annihilation, but for decay it's completely identical except for the particle physics piece and the powers of and the powers of rho at the source. So it has the same particle physics factors that we had before, but now instead of just mapping to the original spectrum, we're going to need an integral over the redshift of emission. We're going to have factors of the density squared, which will now express the distance to the source as a redshift number. And then we're going to have, so there are some other conversion factors that I'll put in a sec, but we're going to have to look at the injection per annihilation at some higher energy, which at some E prime, which redshifts down to the energy that we're actually interested in the present day. So what are the conversion factors? Well, this is now an integral over dz. You want to convert, so you really want to convert this into it, whereas this n squared times sigma v is giving you like a rate, is giving you a rate per volume per time. So that's going to give you, there's a conversion factor between time scales and z scales, is h of z, gives you a factor here. There's also a factor that accounts for the fact that like a co-moving volume, the region over which the number density of photons is conserved, is getting bigger all the time. So even if you're looking at, even if you had like perfectly uniform annihilation that was injecting particles into the universe at some early time, well, if you wait for a long time, the number density of particles in that region is going to drop just because of the expansion of the universe. So that gives you this 1 over 1 plus c cubed factor. If you want to see the derivation of this, so that's qualitatively what happens in this case. If you want to see this worked out in more detail, I wrote lecture notes for TASI that are on the archive from last year, and that has a little bit more discussion of this fact and an example of how it works in the case where you've just got uniform annihilation from the extragalactic dark matter density. Okay, but the key aspects of this result are, it's just similar to previously. The particle physics piece is exactly the same, except that you care about the spectrum at higher energies than the energy that you're measuring today. Okay, so now you know enough to take a dwarf galaxy, take a measurement of the J factor of the dwarf galaxy, and after checking factors of 4 pi and 2 and where they should be, infer from that how many photons or how many neutrinos you should see from a given source. So, so you can now do indirect detection. So what sorts of things might you expect to see when you do this analysis? So often an approach that people take to asking, okay, what sort of signal should I see here? What sort of particle physics should I put in these n gamma pieces is to say, okay, let's just consider the following logic. If my annihilation or decay can produce two-body standard model final states, that will generally dominate the branching ratio. I mean, there may be branching ratios to 3 and 4 body final states as well, but you're going to pay a factor for 3 or 4 body phase space to go to those. So if allowed, two-body standard model states will generally dominate. And so then what you can do is just consider all the possible two-particle standard model final states. Well, particle anti-particle states. So this could be like direct annihilation to electrons and positrons, or to protons and antiprotons, or to Z's, or to W plus, W minus, or to quarks. And then just ask, all right, once those states decayed down, once they produced stable standard model final particles, that predicts a particular spectrum of photons, or you're in the deep non-relativistic limit here. We know the dark matter's cold, so you can just set all the V-dependent factors to 0, and then you can just ask, all right, what sort of photon signals do they make? How does this compare to observations? So okay, so and in general, when you do this, you find that there are broadly 3 different kinds of final state relevant to, from the perspective of indirect detection. There are really about 3 kinds of signal that you can get. So those 3 kinds of signal is 1, and this is what most standard model particles will give you, is some kind of broad, smooth, photon-rich continuum spectrum. So this basically, so this is a broad, smooth photon spectrum. The way that this typically comes about is that if you've got anything in this state that decays through any hadronic channels, when you have hadronic decays, you make pions, because they're the lightest hadronic states. When you make pions, you make neutral pions decay 99% of the time to gamma rays. So this happens for, so this kind of signal happens for tau leptons and all hadronic channels, as well as decays of Higgs and the gauge bosons. So most of the standard model final states, when they decay, there will be some pi naughts produced in the decay, and pi naughts have a gamma-gamma branching ratio of 99%. So for signals like this, so the kind of signal that you're looking for in this kind of final state situation is generally a broad bump. So if I plot power per logarithmic interval versus energy, you're looking for something that looks broadly like this. And the scale of this bump will be determined by the mass, and exactly how wide this bump is will be determined by the mass of the dark matter. But broadly speaking, for all of these channels, what you're looking for to show up in your detector is some kind of broad spectral bump. And so the signature that you search for in direct detection is a bump like this with a morphology that you think is consistent with the spatial distribution of dark matter. That could mean the most probably the most promising low background target for that is the dwarf galaxies of the Milky Way, because they're known to be very dark matter rich and to have not a lot of baryonic dark matter. But there is a signal like this out there in the sky at the moment, Unfortunately, it's at the galactic center, which is a place that is rich in dark matter, but is also rich in backgrounds. So in the galactic center, a signal like this was first seen back in 2009. In 2013, my collaborators and I showed that it actually extended well outside the galactic center, about 1.5 kiloparsecs out from the center, and there's been a lot of effort over the last few years to try to work out what it is. The latest status of that is that I am now pretty convinced that this bump is probably, that a signal like this is probably being produced by a rather unexpected population of pulsars, spinning neutron stars, making gamma rays in the region around the galactic center. Pulsars observationally can make a spectrum that is sort of like this. So for the right dark matter masses, pulsars can be a pretty important background for dark matter models. That said, the distribution of this signal really didn't look a lot like people were expecting from pulsars. So if it's indeed a pulsar population, it is a somewhat unexpected one that we have found. But okay, so this is one scenario. And I should mention that if this is the answer, if something like this is going on, if you see a signal like this, then because it's relevant to hadronic channels, this also often produces protons and antiprotons, charged pions decay producing electrons and protons. So a signal like this, you also predict coincident cosmic ray signals. Second possibility is that you could have very lepton-rich final states. Where by leptons, I don't really mean all leptons, because taus decay and produce neutral pions as well. So I mean electrons and positrons and muons and antimuons. Now, here, these tend to be much harder to find by photon-based direct detection. They're most sensitively constrained by the cosmic ray searches that I skimmed over before. They produce, in photon searches, they could show up in two ways. One is that if you're producing charged particles, then you are definitely also going to produce the things that radiate off charged particles. So at low masses, so our picture here is our miracle occurs, we get electrons, positrons out. We can certainly produce photons by radiating off one of these legs. At high enough masses, you might also be able to radiate Z-bosons off these legs, and at that point you start making this continuum emission again. This kind of final state radiation of photons gives you hard peaked spectra near the dark matter mass. This kind of signal, there's also a secondary thing, which is if you're producing all these cosmic rays, as they propagate through the galaxy, they can radiate photons, or they can upscatter photons. This is often called secondary emission. You can study it by exactly the same J-factor methods that we talked about earlier, except instead of your annihilation signal being your source for the photons, it's the distribution of the cosmic rays produced by annihilation. So these secondary photons can potentially be a big signal and pretty important, but they're often neglected just to be conservative, just because to take them into account you have to know how the cosmic rays propagate. And then you get back to the issue of having to model cosmic ray propagation through our galaxy. The third type of signal that you expect to see in photon searches is spectral lines. So the picture here is just two dark matter particles annihilate to gamma gamma. Since we're in the non-relativistic limit, the dark matter particles are essentially at zero mass. This means that both photons come out with energy roughly equal to the dark matter mass. Or you can also get line signals if it's gamma and some other particle. So this kind of signal is, you could produce a lot of photons. It could be very copious, but the backgrounds are very high. This kind of signal is expected to be small due to the small coupling of the diameter photons, but the backgrounds are very low. There's not really any standard model way to get spectral lines at 1 TeV. There is no way that a pulsar is going to give you a sharp spectral line signal, whereas it can give you these bumps. So most of the searches that you will see, the constraints from indirect detection, from photon-based indirect detection, they will be strong on models of type 1. On models of type 2, they will generally take second place to constraints coming from cosmic rays. And type 3 searches for lions, the constraints on the cross-section will be extremely strong because there's almost no background, but they're usually not that great for actually excluding models just because the rate is expected to be so small. There are some exceptions to that. For sufficiently heavy dark matter, so for like heavy, we know dark matter, which I talked a bit about earlier, the lion signal can actually be one of the most constraining searches, but that has some special factors. So at present, where we stand with indirect detection is that, so at present with indirect detection, so as I said earlier, the CMB bounds constrain thermorelic dark matter with a simple velocity independent cross-section below mass scales of about 10 GeV. If you have one of these photon-rich final states that I just talked about, if that makes up the bulk of your branching ratio, then we can do much better. The Fermi Gamma Ray Space Telescope, which has been up in orbit since 2008, has made many observations of dwarf galaxies. These are low backgrounds environments. They're good places to set robust constraints on these photon-rich channels, and they constrain the thermorelic cross-section for M less than something in the order of 100 GeV, depending on the channel, for these photon-rich channels. So they'll show examples for B quarks and tau quarks, but they produce their full likelihoods and their full data. So if you have a different spectrum that you want to check, you can actually just download the data and check it for yourself. AMS-02 observations of the cosmic rays are a lot more uncertain, but can potentially probe channels which make a lot of antiprotons in this same 100 GeV range. And they can also probe this mass range for the leptonic channels, which don't produce a lot of photons, but do produce a lot of cosmic rays. Above about 100 GeV masses, depending on how much you test the AMS constraints on electrons, they can potentially probe annihilation into primarily electrons at quite high masses, but there are significant uncertainties in the propagation model. Annihilation, if your dark matter model annihilates largely to neutrinos, then all the constraints are at least, I think, a couple of orders of magnitude clear of the thermorelic value at the moment. That is hard to see. On the decay front, these constraints tell us that over a pretty wide range of mass scales, from about the KeV, about the GeV to the eV range, the decay lifetime can be constrained to be longer than about 10 to the 27 seconds. So that's about 10 orders of magnitude longer than the age of the universe. unless you decay straight to neutrinos. So decay lifetime constrained to be I've mentioned a couple of the possible excesses in indirect detection as we went through. There's this excess in the galactic center, which has this, there's a bump in the spectrum at a few GeV. It could be explained by 50 or 60 GeV dark matter annihilating into these photon-rich channels. It's right on the borderline of being ruled out by the dwarf constraints. But we have independent evidence from looking at the photon statistics of that excess that it looks more like a bunch of point sources than a smooth dark matter signal. So my opinion on that is that it's probably point sources. But if you talk to different people, you may get different opinions. There's what's sometimes called the 3.5 keV line. So this is the third type of signal. This is a the simplest dark matter hypothesis there is that this is a dark matter. This is the 7 keV dark matter particle decaying to a photon and neutrino. So that's the gamma plus X. In this case, there are also a lot of variations on this that try to fix some issues with the simple decay hypothesis by invoking a dependence, an effective dependence of the decay rate on the magnetic fields of dark matter. And the difficulty there is that while I said that this signal was really, really low background, well, it's really low background if you're talking about WIMPs. If you're talking about a spectral line at 1 TeV or 100 GeV, it's very hard to explain that in the standard model. If you're talking about a 3.5 keV line, there are actually quite a lot of atomic lines around that energy range. So that is a background that you have to consider. So indirect detection, and it will be very interesting to see over the next few years as we get better X-ray observations what happens to that 3.5 keV line. On the cosmic ray front, there's the large excess of positrons that I talked about. There's also a claimed some slightly significant excess of antiprotons at a mass scale that might be consistent with the GeV excess. It's potentially interesting. It's not very high in statistical, but it's not extremely high in statistical significance, but something to keep an eye on. So indirect detection is an area where there's a great deal of data. The backgrounds are challenging. You have the possibility, I've set some possible questions for this afternoon where you just take the J-factor calculations that we just wrote down and estimate what kind of cross-sections you can get to. But you can see that we're probing the thermal relic cross-section for a wide range of mass scales, and on the decay front, you're probing lifetimes that are much longer than you can reach by any other technique. So, I hope you enjoyed the last 5 lectures on dark matter. I will let you go and get lunch if they've actually brought lunch on time today. Thank you for the good questions. I've enjoyed these lectures. I've enjoyed talking to you. I hope that over the next few years I'll see some, I'll look forward to seeing your papers and your work over the next few years, especially if they have something to do with dark matter, but also if they don't. Thank you very much.